but how do we do sort of calculus with them? Okay, so how do we do calculus? Right. There's sort of the first thing that you always want to define in calculus is the notion of a slope. Right? We want to be able to measure derivatives, rates of change, etc. So we need some notion of what the derivative of one of these parametric curves can be. To get that derivative, I want to remind you what we do in single variable calculus. So in single variable calculus, we measure the change in y divided by the change in x. So there's the top measures the change in the y values divided by the change in the x values. Right, and that measures a notion of slope for us. So to generalize this now to parametric curves, we need to be able to measure rates of change of those two quantities, x and y, for a parametric curve. So we've got some curve. Right, there's our parametric curve, and we want to measure the slope at some point. So what we'll do is we'll measure near that point what the parametric curve is doing. Right? So we can make a small line between one point and another. So we'll call this A and B. And we can measure the change in x and y as we go from t equals a to t equals b. So this gives us a point x of a, y of a, and this gives us a point x of b, y of b. So our corresponding notion of derivative will look something like this. As this point gets closer and closer to A, we get closer and closer to the slope at that point. Okay, and that will measure the change in x, or sorry, the change in y divided by change in x. So that's sort of a generalization of the notion of derivative to these parametric curves. Okay, are there questions there before we go on? So the first thing to notice is that it's not quite clear how to actually calculate this, right? So we need to do some kind of an example. So if we want to find the slope or find the derivative of the thing, we're going to set up a limit we'll get some formula that looks like this. Now we plug in our values here, we get b squared minus 1, b minus 1, and we can calculate some slope. Slope is 2. Yes? Ah, right. Yeah, so yeah, we could have t going to 1 as well. That would be fine. I chose b just to fit with the notation here. Right here I use the notation b. I chose the same notation over there. But you could also write it as t and it would work fine. Okay. Good. Okay, so this is kind of the first principles way of doing things. This is sort of the lots of technical limits way of doing things. I want to point out a clever algebra move that we can do to make this a little bit simpler for ourselves. Right, so in this approach, we need some nice thing to hold, some nice cancellation. I want to point out an algebra move. So this looks an awful lot like the definition of a derivative, right? The thing that we're missing though is this denominator. We would need some b minus a to appear to make this into a usual derivative. So we can introduce that. Introduce the b minus a, and now this turns into the definition of the derivative of each of those parameters, the parameter y and the parameter t. So this gives us a formula in terms of the derivatives of the individual components. Okay, so if we can get the derivative of y and the derivative of x, we can combine them together to give us the total slope. Okay. So we'll rephrase this without taking these limits. Okay, so our second approach to this question goes in the following way. Okay, so we look at the two components. We've got y squared here. Sorry, we've got t squared here. So the derivative is 2t. Here the derivative of t is 1. So we get 2t. Okay, we can use our notion about derivatives in each component to get a derivative for the whole thing. Are there questions there or thoughts there? Yes?
So if we were doing it in the limit form and we would get it in indeterminate form 0 over 0, we can apply the regular like L'Hopital rules and all of
Yes,
those.
yeah. L'Hopital's rule would help you solve this kind of a limit. Yeah, yeah. If you had to work with this kind of a limit, you could use L'Hopital's rule. Yep. Yes, question there?
So to let us have a question on the test or exam, can you go straight to the divide and
Yes. Yeah, yeah. This is a sort of a nice direct approach to it. Yes?
Are there any restrictions for this, or can we use it?
Aha! There, right, the restriction is that this guy can't be 0. So this would not work wherever you've got a vertical asymptote. Or sorry, wherever you've got a vertical tangent. Okay, so that's an important point. Okay, there's one other operation with parametric curves that I want to talk about. So this is the notion of derivatives for parametric curves. We're going to quickly talk about how to get the length of one of these objects. Okay, so if we've got a parametric curve in the plane, right, we want to figure out how long is this thing. You know, perhaps we're designing a piece of trim or, you know, like a bevel on some object, and we want to know how much material do we need. So in calculus, the big idea is that we can approximate things, and when we get finer and finer approximations, we'll converge to the real value of the thing. Okay, so our first approximation will be to add some points to our curve. So we'll say this guy's maybe we'll call this T1, T2, T3, T4. And for each of these guys, we can calculate an approximation of the length. Okay, so we can say that the length of this is approximately the length from here to here, plus the length from here to here, plus the length from here to here. Okay, so to measure, oh yes, question?
When do you know it's like approximate? Like how can you assume that actually close?
Right. So in reality, I'll never ask you to approximate something. We're going to talk about an integral in a moment, and you'll always use that integral. Yeah. But I just want to show you why that integral is a reasonable thing to define. Okay, so for each one of these guys, we have a change in x and a change in y. And we're going to add up those changes in x and those changes in y. Okay, so this measures the length of the segment between T2 and T3. We measure the total change in x